So, good morning, everyone. Thank you for joining our webinar today. So, today we will discuss on FMCW radar measurement and the basics kind of thing. So, we will go further to the slides. So, today it will be the contents of FMCW radar basics, application trends, automotive radar measurement, fundamentals and challenges, automotive radar measurement like chirp signal, receiving chirp signal, generating a chirp signal, transmitter receiver characteristics, and I'll play some example videos where it will be applicable in the real world. So FMCW radar. So FMCW radar is a frequency modulated continuous wave radar, which is widely used in a defense, automation, automotive, and industrial applications due to its ability to accurately measure both range and velocity of a target. If you look at the block diagram of FMCW radar, the radar system generates a frequency modulated signal using a triangular waveform applied to a carrier frequency. This modulated signal is passed through a power amplifier to boost the strength before being transmitted via the transmit antenna. A separate receive antenna is used to capture the reflected signals with a sufficient isolation between the antennas to minimize leakage and interference. The reflected signal is fed into the mixer where it is combined with the original transmitted signal. The mixer outputs both the sum and difference frequencies known as the bit frequency, which gives the range and velocity information. This bit signal is then passed through an analog to digital converter, what we call ADC, and processed in the signal processing block. The final output can be visualized on a display or use it for a further analysis. So next we will talk about the key principles of FMCW. The key principles will be the first one, it will be the continuous wave transmission. Unlike a pulsed radar, FMCW transmits a continuous signal. The frequency of the signal is modulated over time, typically in a linear fashion, which is called as a chirp. Second, the frequency modulation chirp signal. The transmitted signal is a chirp, a waveform whose frequency increases or decreases linearly over a time. The third will be the bit frequency. The received signal is a delayed version of the transmitted chirp due to the round trip time to the target. Mixing the transmitted and the received signals produces a bit frequency. This bit frequency is used to calculate the range. The fourth is a range calculation based on the time and delay between the transmitted and received signals. The fifth is the Doppler shift for a velocity. If the target is moving, the received signal also has a Doppler shift. By analyzing the multiple chirps, example in a frame, the Doppler frequency can be extracted to estimate a velocity. The sixth will be the range Doppler processing, where we will be using a 2D FFT, fast Fourier transform. First FFT extracts the range from the bit frequency. The second FFT extracts the velocity from that Doppler shift across a chirps. The seventh will be the resolution and a bandwidth. The resolution range depends on the bandwidth of the chirp. The velocity resolution depends on the chirp repetition interval and number of chirps. So when you further, we will talk about the frequency time relationship in the FMCW radar, how the frequency and the time analysis can be done. So in the waveform diagram, the transmitted signal is represented by the bold line, while the received signal is shown as a dashed line. When a target is moving towards the radar system, the beat frequency is influenced by both the range and the Doppler shift, where FR range frequency component and FD is a Doppler frequency component. The beat frequency is given by FB is equal to FR plus or minus FD. During the raising edge of the chirp upward sweep, the frequency difference is narrower due to the target approaching. This is referred to as the upward beat frequency, where we will be notifying that FB is equal to FR minus FD, and we will consideration as a equation 1. During the falling edge of the chirp, the downward sweep, the frequency difference increases, as we see in the waveform. So FB is equal to F down is equal to FR plus FD. We will take this as the equation 2. So once if we add the 1 and 2, we get a range frequency, and we subtract the equation 1 and 2, we get the Doppler frequency, which we call it as a which will give the information of the velocity of the target. So let's continue with the application trends where we will be using the FMCW radars. So there are as we go on, the technology goes, the modern communication and radar systems operate across a wide range of frequencies, like wireless communication technology, where the standard IEEE 802.11ad utilizes the 60 GHz millimeter wave band. 5G technologies operate in both a sub-6 GHz and millimeter wave bands, 24 GHz to over 100 GHz. The automotive radar typically functions in the E band 55 GHz to 90 GHz. Weather radar covers a broad frequency spectrum from S band 2 GHz to W band 110 GHz. To accurately model and simulate passive components such as inductors, capacitor, and resistors, it is essential to perform a wide frequency sweep, starting from near DC, a few hertz or kilohertz, and extending well beyond the highest harmonic of interest. Tools for characterizing these RLC components, we will be using the network analyzer. Which has a wide band sweeps to extract broadband equivalent circuit models. So when you come for next, we will talk about the radar applications like radar applications. The frequency modulated continuous wave radar is gaining a widespread adoption across various sectors due to its high resolution, low power consumption, and reliable performance in all weather conditions. Example in foreign object debris, like detection at airports operating in the 76 to 77 GHz band, FMCW radar is ideal for detecting small objects on runway. Its high resolution and safe operation make it suitable for continuous monitoring in diverse weather conditions. Second, the train control and safety system. FMCW radars is increasingly used in a collision avoidance, obstacle detection, and automated train operations. Its ability to measure both the range and velocity, and it ensures enhanced safety and operational efficiency in the train. The third, it will be the ice and snow monitoring in mountain regions, where the FMCW radar is proving effectively for measuring the thickness and analyzing the snow stratigraphy. So estimation of a snow water and equivalent SWE. So the fourth will be the metal detection, the differentiation between the metal detection part, where it will be where you will use the CW frequency and measure where you will differentiate the metals characteristics, like what is the metal characteristics, like what is the properties, like electrical properties and magnetic properties of the metals, and we will come to know what is the where you will be differentiating the metals. So next we will talk about the application trend further to a gesture. 60 GHz FMCW radar is cutting edge technology widely used for a gesture recognition and short range sensing in consumer electronics, automotive, and industrial applications. Frequency range typically operates between a 58.5 GHz and 62.5 GHz. For a better resolution offers a millimeter wave protection, precision, like example 37.5 mm range resolution, and can detect objects within a 1 to 2 meters, ideal for gesture sensing. So 77 to 81 GHz digital modulation imaging radar systems represent the cutting edge of radar technology, combining a millimeter wave frequencies with advanced digital modulation and MIMO architectures. to deliver high-resolution 3D imaging and capabilities. The frequency band it operates in 76 to 81 GHz millimeter wave band, offering a wide bandwidth up to 4 GHz for a fine range resolutions. Modulation techniques uses a FMCW and a PMCW continuous high resolution scanning digital code modulation for the digital modulation radars. In a MAMO architecture, some systems like Handor S8, S80 radar on chip support up to 192 virtual channels using a 12 transmitter and 16 receiver antennas. Portable and compact radar solutions operating in the 57 to 64 GHz band, ideal for a short range, high resolution sensing applications like single chip 57 to 64 GHz radar sensor, precision 60 GHz MIMO radar, proximity sensing, industrial automation, and consumer electronics. Nowadays, the FMCW is for a thermal wind profiling in atmospheric studies, especially in the boundary layer and mountains regions are used. During the COVID-19 pandemic, radar sensor technology found innovative and impactful applications, especially in the healthcare and public safety. Here are some of the most notable uses, like non-contact vital sign monitoring radar systems, particularly a Doppler and FMCW radars were deployed to monitor the respiratory rate, heart rate, body movement. Those systems enabled a continuous contactless monitoring of patients in isolation wards, reducing the risk of various transmission to healthcare workers. And self-injection locked radar is in isolation wards, social distancing and occupancy monitoring, cough and monitor movement detection. More advanced radar systems could detect a coughing patterns and sudden body movements, which are potential indicators of respiratory disasters or falls in the isolation setting. Utilizing a AI-enhanced health monitoring to detect abnormal trends in a vital signs today and in future medical applications. So Andritso supports all those emerging applications related through the instrumentation and R&D in those areas, be it a millimeter wave testing, broadband device characterization, or FMCW radar-based sensing and detection, or the newer frontier areas in sensing and healthcare with our VNS, signal generators and spectrum and signal analyzers. Now we will go deeper into the core applications of FMCW and radars. So automotive radar measurements using our MS2760A ultra portable spectrum analyzer. In this section, we will briefly talk about the fundamentals of automotive radar, including the technology growth. We will discuss the measurement challenges and also their solutions. The adoption of FMCW radar in automotive and ADAS systems has experienced a significant growth with a compound annual growth rate of 23.81%. The market expanded from USD 2.27 billion in 2016 to an estimated USD 15.52 billion by 2025. In a non-automotive application such as object detection, the FMCW radar market is projected to grow from USD 1.5 billion in 2023 to approximately USD of 4.2 billion by 2032, reflecting a compound annual growth rate of 12.5% in a non-automotive applications. So the major trend is ADAS trend, where higher frequency of the outside in and more sensors are used. The ADAS, like advanced radar, advanced driver assistance systems, landscape is rapidly evolving because of its higher frequency radar outside in sensing, shift to 77 to 81 GHz and beyond. Those bands offer a finer resolution and longer range, enabling a better detection of small and fast-moving objects. In outside architecture, sensors are increasingly placed around the vehicles in bumpers, mirrors, roof to create a 360-degree awareness zones. Benefits: improved object classification, enhanced performance in adverse weather, better support for autonomous driving features. More sensors, more modalities. Sensor fusion combining radar, LIDAR, cameras, and ultrasonic sensors for robust precision, redundancy, and diversity. Multiple sensors ensure a reliability and accuracy even if one fails or is abstracted. Examples like radar for a velocity and range, cameras for object recognition and land detection, LIDAR for 3D image mapping, and ultrasonic for a close range parkings. So FMCW based motion sensors inside a car cabin are designed to detect and monitor occupants with a high precision, offering a range of safety and comfort features. Key applications like child presence detection detects micro movements like breathing or slight shift, alerts if a child is left behind in a parked vehicle, works with blankets or clothing even in a low light. Occupant monitoring identifies number of a position of the passengers, adjust airbag deployment and seat belt tension accordingly. Enhances a comfort systems. Driver vital sign monitoring tracks a respiration and heart rate, detects a fatigue or a medical emergency, supports autonomous driving safety protocols, and a gesture recognition, as I told in the previous slide, enables a touchless control of infotainment and climate systems, and recognizes a hand movements like sweeps, taps, or holds. So the automotive radar bands, the 24 gigahertz frequency band traditionally used in automotive radar systems is being phased out in favor of the 76 to 81 gigahertz band, which offers a higher resolution and better performance for advanced driver assistance systems and autonomous driving. Furthermore, ongoing research is exploring the potential of expanding a radar sensing technology beyond 100 gigahertz, aiming to unlock even a finer spatial resolution and enhancement object detection capabilities for a next generation automotive applications. Automotive testing encompasses three key aspects: signal generation, signal recognition, and the characterization of both the transmit and receive components, including antenna transceiver modules. Those are typically performed using a signal generator, vector network analyzer, and spectrum analyzer. The chirp signal are at the center of the automotive radar testing, which is used to generate the chirp signal. A chirp is a type of a waveform in which the frequency gradually increases or decreases over a time. When viewed on an oscilloscope or a frequency versus time plot, a chirp appears as a smooth sweep from start frequency to a stop frequency. This sweep defines the bandwidth of the chirp, and the rate at which the frequency changes is known as the chirp slope. In FMCW radar systems, this modulation allows a precise measurement of distance and velocity by analyzing the frequency difference between the transmitted and received signals. As we expand the concept of chirp signals, it's important to understand that they are often transmitted in a repeating sequences. Each individual chirp has a defined chirp time, and a sequence of multiple chirps forms a chirp frame. Depending on the application, a frame may contain anywhere from 32 to 256 chirps or more. Between each chirp, there is a brief idle time, and the chirps within a frame can vary in characteristics. Some may have a narrower slope, while others may have a wider slope, affecting a resolution and the range. After a chirp frame completes, there is a typical and off time before the next frame begins. This off time is intentionally designed to improve the power efficiency and reduce the heat generation in the module, especially in the continuous operation scenarios. The characteristics of radar chirp or FMCW significantly influence its performance and determine its suitability for different applications. For example, a chirp with a narrow slope but wider bandwidth provides a better range resolution, which is ideal for applications like brake assist, where it's crucial to quickly and accurately detect a nearby objects. On the other hand, for applications like adaptive cruise control, where the target vehicle is typically further away, you can adjust the chirp slope to prioritize the maximum detection range over a resolution. In essence, by modifying the chirp parameters such as a slope and bandwidth, you can tailor the radar's behavior to meet the specific needs of each ADAS function. So measurement challenges. FMCW radar signals are highly specialized and can be challenging to measure due to their rapidly changing frequencies and wide bandwidths. For example, a continuous wave signals in FMCW radar sweep across a broad frequency range very quickly. A modern automotive radar system typically operates in the 76 to 77 gigahertz band with a 1 gigahertz bandwidth, and some advanced system extend up to 81 gigahertz, which is a 4 gigahertz bandwidth. Analyzing such a wideband chirp is difficult with a conventional spectrum analyzers, which may struggle to capture the full signal accurately. Additionally, because radar systems operate at a very high frequencies, the equipment required to measure and analyze those signals must have a high dynamic range, wide bandwidth, and fast sweep capabilities. Those requirements make radar signal measurement both technically demanding and resource intensive. When testing a FMCW signal using a traditional spectrum analyzer, the ability to capture the signal accurately depends on both the characteristics of the chirp and the analyzer's sampling speed. A typically spectrum analyzer uses a sweep-tuned sampling process, which can introduce a blind spots during a measurement. If the chirp signal changes a frequency rapidly, parts of the signal may fall outside the analysis window. As a result, you might observe a gaps in the frequency trace. Rather than continuous waveform, this can make it appear as though the signal is missing or intermediate. To mitigate this, you can to mitigate this you can use the say spectrum analyzer, ultra portable spectrum analyzer. The challenge too will be the image rejection. With MS2760 spectrum analysis in FMCW analysis, unlike traditional spectrum analyzers, the MS2760 lacks in front-end filtering, which represents the challenges in accurately analyzing FMCW, frequency modulated continuous wave signals. In a conventional spectrum analyzer, signal processing involves a multiple sampling stages, where sampling must align precisely to display meaningful results on the screen. However, in the MS2760A, we use a image rejection via software due to the absence of hardware filtering. Sample mismatch between the processing stages can lead to inaccurate or flat traces. As a result, many FMCW signals fail to appear correctly, often displaying as a flat line, providing no useful diagnostic information. This limitation makes it difficult to characterize a radar signals effectively, especially in applications requiring a precise pulse analysis. A better solution for analyzing FMCW signals is to use a real-time spectrum analyzer, RTSA. As shown in the screenshot, an RTSA can clearly display the uniform frequency sweep of a FMCW signal both upward and downward, make it an excellent tool for visualizing chirp characteristics. However, one limitation of real-time spectrum analyzer is their analysis bandwidth. While they are effective for signals with bandwidths like 1 gigahertz, analyzing wider chirps such as a 4 gigahertz or even 10 gigahertz in future radar systems requires analyzers with significantly higher bandwidth capabilities. To capture such a wideband signals in real time, you need a high-end expensive instruments, although you can set a wider frequency span or a traditional spectrum analyzer. But doing so introduces blind spots, which can result in incomplete or inaccurate signal representation. One of the most common lab setups for testing FMCW wider signals involves using a signal analyzer in the combination with an oscilloscope. In this setup, the oscilloscope samples the chirp in a real-time, capturing all variations within the chirp. This data is then broken down and analyzed to extract the key parameters. such as a chirp slope, frequency, linearity, and other critical characteristics. This method enables a comprehensive analysis of the radar signal and is considered as an excellent solution for the depth RF evaluation. However, the downside is that this setup is often a very expensive, bulky, complex, and for customers who do not require such a high level of detailed testing, this solution may be overkill, both in terms of a cost and practicality. So this brings to our fourth challenge, the cost. What do in such a situation? Well, how about the something cost effective, capable and very portable which can handle all the test parameters requirements in a small form factor? Introducing a Unriso ultra portable spectrum analyzer. The ultra portable spectrum analyzer from Unriso can do all the testing related to FMCW automotive radar application. Let's take a look at the measurements. The first major step in enabling a valuable measurements for automotive radar using the MS2760A spectrum analyzer was the introduction of minimum capture time. This feature plays a crucial role in ensuring a complete signal acquisition. What minimum capture time does? It extends the duration of each sample, allowing the analyzer to hold the signal longer before moving to the next processing stage. By setting the capture time equal to the frame period of the radar chirp, the analyzer ensures that the entire chirp signal is captured within that time window. Impact on FMCW analysis. This approach prevents a signal rejection and ensures that the full trace of the chirp is visible on the display. For example, with a 100 millisecond frame period, the analyzer captures the full signal and then starts again for the next part. This process is repeated at every 20 megahertz frequency step from the start frequency to the stop frequency, ensuring a compressing coverage. Sweep, sweep trace analysis in radar testing. Once the frequency sweep trace is completed, key parameters such as the envelope flatness, start frequency, stop frequency can be observed. Envelope flatness indicates the consistency of the signal amplitude across the sweep range. Start and stop frequency defines the boundaries of the sweep, essentially to verifying the radar's operational bandwidth. This analysis helps ensure a signal integrity and performance across the desired frequency range. As the next step in the radar signal characterization, we utilize the zero span mode on the MS2760A spectrum analyzer to gain a deeper insights into the chirp behavior. What is a zero span mode does? Zero span mode allow you to observe the time domain behavior of the signal at a specific frequency. Instead of sweeping across a range of frequencies, the analyzer locks onto a single frequency and displays how the signal varies over a time. Application in FMCW radar. When applied to FMCW radar signals, zero span captures the cross-section of the frequency range. You will observe a continuous wave pulse appearing each time in a chirp occurs. This helps you visualize the timing and repetition of the chirps, especially useful when you're analyzing a frame-based radar signals. Once you have identified the frame period of the radar signal, say by measuring the time between the marker 1 and marker 3, you can determine the duration, which in this example is approximately 50 milliseconds. Knowing this frame time allows you to set an appropriate capture time to ensure a complete signal acquisition. Zooming in the chirp resolution. By zooming into the captured signal, you can observe a multiple peaks within the frame. Those peaks represent individual chirps. In this case, you will see a 32 chirps per frame, and each chirp is clearly distinguishable within the 50 millisecond window. This method ensures accurate visualization and analysis of radar chirp structures, which is essential for validating a signal integrity and timing. When you come for generating the chirp signal, to generate a chirp signal using the rubidium signal generator, we enable both a pulse modulation and frequency modulation simultaneously. Here how the process works. Step 1, the pulse modulation setup. We begin by configuring a pulse modulation. The pulse width defines the duration for which the signal remains on. The pulse period, also known as the pulse repetition interval, determines the time between the consecutive pulses. We set the pulse width equal to the desired chirp duration and the pulse period equal to the chirp repetition interval. Step 2. Frequency modulation setup. Next, we configure a FM modulation using a ramp waveform. The ramp start is synchronized with the start of the pulse. The ramp duration is set equal to the pulse width, ensuring the frequency sweep occurs during the pulse. Step 3. Chirp generation. By enabling both a FM and a pulse modulation with a synchronized timing, the generator produces a chirp signal, a frequency sweep that occurs during each pulse. This setup ensures a precise control over a chirp timing and frequency characteristic, ideal for radar signal simulation and testing. So you can see the simultaneous and synchronous FM and a pulse modulation created using a chirp. This setup is the demonstration for generating a chirp waveform. The RF output of the rubidium signal generator is connected to the MS2090A unrestricted spectrum analyzer. Additionally, the FM and pulse baseband outputs from the rubidium generator are routed to an oscilloscope, allowing us to observe the baseband waveforms used for a internal modulation. All instruments, the signal generator, the spectrum analyzer, and oscilloscope are connected to my laptop via the Ethernet switch. This configuration enables a remote GUI across for each device, allowing me to control and monitor the rubidium waveform generation and spectrum display directly from the laptop. The transmitter and receiver antenna, the antenna transceiver modules and associated components in automotive radar systems require testing and characterization similar to our RF devices. This can be effectively performed using a vector network analyzer. We are conducting a far field antenna measurements using the E-band shockline vector network analyzer. This setup enables a precise characterization of antenna performance at higher frequencies, ensuring a accurate S parameter data and radiation pattern analysis, essentially for automotive radar and other advanced RF applications. We are utilizing our E-band shockline VN vector network analyzer to perform a S parameter measurement on automotive radar systems. The setup includes an integrated high-frequency cables extending up to device under test, such as the RF radar module, ensuring accurate and reliable characterization across the entire signal path. So, what is the rubidium signal generator? And what is the best key highlights in the rubidium signal generator? When you come for a signal generator, we are having a best signal purity and we are having a higher output power. We are having a better, wider frequency coverage, atomic grade frequency stability, on-site level calibration, comprehensive pulse modulation where you can generate a pulse train kind of thing, and user-defined waveform generation and modulation to generate a user-defined waveform, arbitrary waveform. And there is a legacy of interface support like GPAB and LAN and USB for programming. So when you come for Yanritsu MS2760 ultra portable spectrum analyzer, it is having a FFT analyzer with a non-linear transmission line technology, which start from 9 kilohertz up to 170 gigahertz. So we are having different variants start from 32 gigahertz, 145, 170 gigahertz, the models. It measures the channel power, adjacent channel power, and occupied bandwidth as a standard measurements with a plus or minus 0.5 dB of amplitude accuracy. Fast sweep speed makes it most applicable for application related for automotive applications. And it has a greater than 103 dB dynamic range at 70 gigahertz typically. So I will run some examples where we have used the ultra portable spectrum analyzer in automotive applications. Just see the video.
Hi, my name is Kirby Hong. I'm a product marketing manager at Emitsu Company. Today I'm here to show you how the ultra-portable MS2760A spectrum analyzer can make measurements on a millimeter wave FMCW automotive radar. In this setup here, I have the MS2760A directly connected to a horn antenna that is looking into a radar evaluation module from TI. The module is configured by software running on this tablet here. It is configured to send out a 1 gigahertz chirp from 76 gigahertz to 77 gigahertz. The chirps are organized into frames, each frame having 16 chirps. The frames repeat at a 20 frame per second rate. The first measurement that I want to show you are time domain measurements in zero span mode. Since the frame rate was 20 frames per second, we expect to see the frames repeat at a 50 millisecond period. So here in zero span, we have a 100 millisecond sweep time, so we expect to see
Okay. So now we support for all the steps like evaluation of a phase. Our experts are present to support delivering our solutions and evaluation in operational solutions situations, and in integration phase, automation and integration in existing procedures. And we will provide a training like in a started and advanced user sensor sessions. And we are having accredited calibration and repair center at Bangalore and Noida branch office with and at Hyderabad. So for more information, you can visit our website, the www.andriso.com. And for any thanks for any technical support, you can visit our Andriso solution team. And for a product marketing information, you can go for a Asian underscore Markham at andriso.com. For a sales queries, you can contact Asian underscore sales 2 at andriso.com. Thanks for your attending the webinar.